Hello students and fellow staff members. Welcome back to another session of Introduction to Programmable Logic Controllers. My name is Vasan Naika and I'm from the TVET College in Pietermaritzburg. Now, in the previous lessons, I discussed the basic uses of PLCs, how the PLC works, the PLC block diagram, as well as the PLC scan cycle. And then we looked at logic gates, which are the two logic gates, your AND and your OR gate. And then we had started PLC terminology. So I'm going to continue with PLC terminology today, as well as discuss the different programming languages and also basic PLC circuits. Right, this is where we actually stopped at the last session. So I'm going to take off from here. We discussed the start button, which is a normally open switch, and we said in industry it is normally green. And normally open means it's an open contact in its normal state. We also mentioned the fact that it is a push button switch, which is actually spring loaded. All right, so if I press and leave it, it makes contact, it breaks contact. Okay, it's not like a toggle switch that stays. Okay, we then said the PLC circuit symbol for your start button is just two lines, okay, and that would now represent a normally open contactor. When I pressed that switch, I refer to it as energizing the start button. I know it's a very loose term that I'm using, but I'm going to use it continuously in the programming section, so you won't get lost, or you'll understand, or you'll be able to follow me if I start using it now. So when I energize my start button, you'd find it moves from a normally open contactor to a normally closed contactor. And this symbol here with the two lines on the sides represents a normally closed switch in PLC terminology. If you look at now the stop button, once again in industry I've mentioned that the stop button is normally red. It is a normally closed contact, so it is represented by a switch that's closed. It is also a push button or a push to make kind of switch where in its normal state, okay, it is normally closed. If I press it, it actually breaks the contact and now it becomes normally open. So if I energize the stop button, it actually becomes a normally open switch. Now, attached to your PLC input modules, as we discussed previously as well, there's a lot of sensors, which we call your PLC field devices. All right? Remember, your start and stop buttons are also referred to as input sensors. I will continuously use that terminology as well. Then you have your emergency stop, which is also input sensor. You have your proximity sensors, you have your infrared sensors, metal detector sensors, and temperature sensors, etc. Whatever is connected to the input module of your PLC. Now, these sensors can have or be in one of two states. They can either be normally open or normally closed. So I've listed both of them here. If they're normally open, they will be represented as an open switch. And if they're normally closed, they're represented as a closed switch. So in the normal state, okay, if it's normally open, then I energize it, or if you look at if it's a proximity sensor or a metal detecting sensor, if a piece of metal comes past, if it's normally open, we say the sensor is energized, and then it'll close, and then be represented by a normally closed contact. If on the other hand the sensor is normally open, when energized, it'll close. Now, if I look at, if on the other hand the sensor is normally closed, when energized, it'll open. If I now look at your output devices or your output coils, your output coil could be in one of two states. It could be normally open and normally closed. Now, these are output coils. I'm going to discuss this a little bit further just now, but just to give you the terminology first, your output coil is represented by this symbol. It's similar to brackets, okay? And associated to this coil, I could have additional contacts. Now, they could be either normally open contacts or normally closed contacts, as we will see when we are programming. And once again, if the output coil has a normally open contact associated with it, when it's energized, it closes. And if it has a normally closed contact associated with it, when it energizes, it opens. I've listed all of those for you in the table as well. I'm then going to look at timers. Now, your timer, once again, is also an output device, or it's part of your output module. When these timers are actually not your electrical field device timers, these are built-in timers that are built into the PLC CPU, all right? And associated with these timers as well, you could have additional contacts. And once again, a timer could have associated with it a normally open contact or a normally closed contact. There are two types of timers. I'll discuss that just now. It's your on-delay timer and your off-delay timer. However, if a timer has a normally open contact associated with it, you will find when that timer is energized or when it counts down, when the timer is elapsed, you'll find that contactor will close. If it's a normally closed contact associated with the timer, then the timer contact would actually open after the specified time. Now, as I mentioned earlier, there are two types of timers. Your on-delay timer, and in your on-delay timer, you will find your timer will actually energize after a specific period of time. I'm just going to put that here for you. Okay, so your on-delay timer will time first, and then it will energize. Your off-delay timer will energize first. And then de-energize. Okay, so after your specific time, if it's an off-delay timer, let's say, for example, it's a 10-second timer. If it's an on-delay timer, it will time 10 seconds and then energize. If it's an off-delay timer, it will energize immediately and after 10 seconds go off. All right? Two different timers used for two different purposes or many different purposes in PLCs. Now, before I actually look at some programming or ladder diagrams itself, I want to actually get rid of a misconception that most people studying PLC have. When we represent an output, or we refer to this as an output coil, all right? Output coil or output contactor. Okay. Most people actually think that it is the same sort of contactor or relay that I've listed in the diagram here, which are actually your field devices. So please remember that your output coil is not a contactor, it is not a relay, it is not a field device. It actually represents the diagram that I've drawn in the center here. It is actually an electronic switch, and just to explain that, you'd find from your processor itself, all right, you get 5 volts DC. All right, I just want to explain that. What this actually represents. This is from the PLC processor, which is your 5 volts DC, okay? So once I have current in here, that means this specific output is turned on. You would find that this LED would actually turn on. Once the LED turns on, you know it's a light emitting diode. It will emit light. And this is attached to a phototransistor. Okay? And you can see that there is no physical contact or physical connection between the LED and the phototransistor. So we call this an optical, okay, because I'm using light, isolator. All right, that transistor there now is used to switch on. A triac, which we call an electronic switch. And that triac is now part of your output device. So to complete the circuit, all right, normally here you'd have a fuse, okay, and this is your live or your supply. Okay, and at this end, I will have, let's just say it's a lamp, which is now my field device. Okay, if I'm using a 24 volt field device, like these lamps here, 24 volt lamps, I'm going to have a 24 volt supply here. If I'm using 220 volts, I'm going to have a 220 volt supply here. Some PLCs can handle up to that depending on the output module. If you remember previously, I've discussed that the output modules for this particular PLC operate on 24 volts. So this whole circuit here, all right, represents now what we call my output contactor or my output coil. Remember, it is not a physical contactor, it is not a physical coil. Attached to that output, you would find you could have as many normally open or normally closed switches that you want that are built into the PLC. So once again, please remember that your output coil in a ladder diagram does not represent a contactor or a relay. Your contactor and relay, for example, I could have, instead of a lamp here, I could have a contactor here, a 24 volt contactor to switch on a motor. I could have a 24 volt relay here, like you would see later on, to switch on lights. I hope that brings some clarity on the symbol of the output coil. All right, now that we've discussed the PLC terminology and we understand or have a basic understanding of timers and also your output contactors or your output coils, as we refer them to it, let's look at PLC addressing. Now, your PLC itself does not understand the word start or stop or sensor 1, etc. All right, so if I had to just write this down here, if you had to program the word start into a PLC, it wouldn't know what you're talking about, all right? What you have to do is to your start button, we have to assign an address. Okay, this address represents a specific input in the input module. Now, there's different types of addressing. If you look at the table that I've listed, for your input addresses, okay, you could use I0.0, or you could use X0.0, or you could use X0.001. Or in some of your textbooks, it's just X001. And similarly, for your output devices, depending on the type of PLC that you're using, your outputs can be represented by Q0.0, Y0.0, or Y001. The important thing here to note for your specific course is that all your inputs are represented by X's and all your outputs are represented by Y's. The reason I've included the I and the Q for inputs and outputs, you will find when I'm programming the PLC, the Siemens PLC, we actually use I for inputs and Q for outputs. The other names that you have associated with your inputs and outputs, for example, your start or your stop or your sensor, are referred to as symbolic names, okay? And you'll find in your PLC or in your program manager, there is a way to actually associate your symbolic name to your PLC address so that it appears in your program. I will show you that a bit later. For this particular PLC, I'm just going to discuss this briefly so you have an understanding of your input and output addresses. I mentioned earlier on that it says here that it's an DI32 DC 24 volts, okay? It says DI32 DC 24 volts. Okay, what this means, it actually has 32 inputs that operate on 24 volts. Okay, the particular addresses for those inputs are assigned in your hardware. When you're actually configuring your PLC, you assign addresses to your input modules and to your output modules. I'm going to show you later on how to get to the hardware configuration, but for now, I'm just going to explain, because I'm going to use these inputs and outputs just now. Your digital inputs have addresses from 0 to 3, okay? What this actually means, all right? Remember, I've got 32 inputs. So what that actually means is your first input would be I 0.0, the second one would be I 0.1, and going down to I 0.7, okay? And that would give you my 8 input addresses. Now it says it goes from 0 to 3. So the second 8 would be I 1.0, I 1.2, going down to I 1.7, and that would give me another 8. Okay, so those are my 16 input addresses associated with that module, but it said it has 32. So similarly, the fourth set would be I 2.0, I 2.1, I 2.2, going down to I 2.7, and that's another 8. And finally, it will be I 3.0 to I 3.7, and that would give me another 8. And you can see here where the 0 to 3 comes in. Those are all 0, those are all 1, those 8 are 2, and those 8 are 3. You could obviously change those addresses when you are configuring your PLC, but for now we are not going to do that. I just need to explain to you the 32 input addresses. The other thing you have to know is that no two input devices will have the same address. Every single switch, every single sensor will be connected to a different input, all right, and it would have a different address. And that is how your PLC is actually able to differentiate between your start button and your stop button. Remember, it doesn't know that you've pressed the green button. It will just know, okay, there's 24 volts at input 0.3, okay? If my start button was connected to input I0.4 and I press it, you will find it will just know, okay, the 24 volts that was at 0.4 is now being removed. That means the stop button has been pressed. So that is how the PLC would actually detect changes in inputs, by looking at the inputs, addresses, and look at what changes have taken place. All right, I'm now going to look at the different types of programming languages, and I'm going to start with FBD, which is your function block diagram. If you look at this, these are actually logic gates, and your program is actually written using logic gates. So using logic gates to write PLC programs is actually the reason you study logic gates, or the reason I've discussed logic gates before. However, for your particular course, you're not going to use FBD or function block diagram, where you're going to use ladder, as I will discuss just now. The second type of programming language is statement list, or STL. Now, this is programming language that are written in statements or logical statements in a logical sequence from top to the bottom. Most people find this the most difficult, but however, there are programmers who find this the easiest. So it all depends on what you are actually used to and what you learn to be the best for you. Now, the one that you need to know and need to understand fully is ladder diagrams. The three diagrams that I've shown you so far are identical, but if you look at the ladder diagram now, the reason you actually use it for programming is that it is quite similar to the way you'd actually write up electrical programs in industry. The reason it's actually called a ladder diagram, if you look at it, all right, it has rungs. Now, we call these rungs, each rung represents a different line of programming. So if you look at the diagram in front of me, I've got the first rung where I've got two inputs in parallel. I've got an output coil, and I've got an output timer. All right. In my next rung, I have a normally closed switch. I have another output coil. In the third rung, I have a normally open switch, and the fourth rung, a normally open switch and another contactor. And finally, I have one more rung with an open switch and another contactor. In your ladder diagrams, when you're actually ending it, for your practical purposes, you need to put an end statement, although when you're actually practically programming PLCs, in some PLCs it is not required. We discussed the scan cycle previously, and the scan cycle actually represents the way your PLC or the CPU actually looks at the program that you've written. All right? You will find that it will look at the program from top down. All right? That means from the top of the ladder moving down, and also from left to right. So we said previously that your left column here represents your live, and the right column represents your neutral or your normal. So when the PLC actually does its scan, it will go to the first rung and check, are there any changes to X or input X001? If there are, all right, then it will look at what does it do? Oh, it's going to energize contact 003. It will then send the required signal to the output module to make the changes. For example, turn the motor on. And as I said, it will continue going through the program from top to bottom observing all the changes, and then making the necessary adjustments to your output modules. This is just a brief intro on ladder diagrams. I know it's a bit new to you, but I'm going to discuss them further in detail so that you understand exactly how they work and you'd be able to do your own. Okay, now that we've discussed the different types of programming languages, I'm going to just run through a simple program and explain to you how to actually understand what the program does. So if you look at the program that I've got up on the screen, I'm just going to draw it on the board. Open. And okay, so that is the diagram. I've just redrawn it on the board so I can explain it to you. I've got 3 lines of programming. Okay, remember, I've got an input, and I've got 3 output contactor coils. Attached to this contactor coil is motor 1, and attached to the second or the third output contactor coil is motor 2. Now, the important thing to look at here is that the addresses of this normally open switch is Y001, and the address of this switch, which is normally closed, is also Y001. These 2 switches are the additional contactors that we spoke about earlier on that are associated with that contactor coil Y001. Okay, so before you actually look at what does the circuit do, you need to understand how it actually operates in its normal state. So in my normal state, that means nothing is pressed, nothing is energized. What happens? If you look at it, remember we said current will flow from left to right. This is normally open, so nothing would flow through there. This would be off. This is normally open, nothing would be in that rung, so that motor would be off. However, this switch is normally closed, which means current will be allowed to flow through that rung. Y0.03 is energized, and motor 2 will be on. So in its normal state, motor 2 would actually be on. I'm going to stop there for now, just to give you a chance to actually practice all that we've done. As I said, unfortunately, you may know that I'm going through stuff a bit fast, but it's due to time constraints that we have very limited time to do a lot. I will take off from here the next time I see you. So for now, please stay safe, stay at home, look after yourself, and look after your loved ones. Thank you.